All right, Unit 2. Limits and continuity. I like my quote. I've been a stranger in a strange land. You're going to start thinking and acting in very different ways. So here's what we're going to do this chapter. We're going to calculate and know the difference between average and instantaneous rates. I don't find that very challenging. We're going to understand the definitions and properties of limits. This is somewhat tricky. There's just a lot of ticky-tack stuff to remember. You're going to calculate limits involving infinity. You've already done this. It's called an asymptote, a horizontal asymptote. And then they start getting into vertical and horizontal. Horizontal are limits, vertical are something else, but you can take a limit as you get closer and closer to an asymptote. It's pretty goofy. And understanding continuity, they make a big deal out of it for important reasons, but it's also goofy. And you're going to do the intermediate value theorem, which is ludicrously easy. And then we're going to get into computing tangent lines. We're actually going to do a little calculus. And this is it. Can't do this. Don't take the rest of the course. Absolutely critical, you know it. So rates of changes and limits. So this is calculus things. There are 4 things this year. There are limits. There are derivatives. There are integrals. And then there are infinite series, and they are all related. Limits are used in derivatives and integrals. Infinite series use derivatives and integrals. Derivatives and integrals are inverses of each other. Yeah, you're gonna really break your brain this year in terms of understanding all this stuff, but we'll get you there. So first off, how do we calculate average velocity? Now, this is the first day of real calculus. Everything up to this point was just review. And I find this funny. This was actually on the AP problem I graded last year, and the whole world blew it. It was shocking. All right. So average velocity is the change in position over the change in time, which is y's position, or f of t is position. So I'll just call it f of t. I'm going to leave that for a second. So how much do we change time? Some gap h, yh, no idea. We just decided to use h. That's an h, not an n. So on the top, it's the time we had plus h minus time. So you could actually do time plus h minus time. They cancel out. You're just left with h. If this is confusing to you, don't sweat it. We're going to do it so often, you'll eventually get tired of it. So here's our first 2 seconds. Now, since we're starting at 0, we don't need all this other stuff. We'll put it in, but so hey, what's the velocity? Average velocity. Okay, well, 16 f of 2 minus f of 0 over the gap. 32 feet per second. When we take a derivative, and this is where we're heading with this, we take the position, we add a unit on the bottom. Taking it with respect to time, we add seconds. I'm just astonished at how much I'm telling you that is going to be with you all year, and people are like, yeah, sure, I don't quite get it, but I'm sure I'll figure it out. And you really want to figure it out now. So now, how do we find the instantaneous speed, the speed at any instant? Well, if we look at the average speed formula, just delta y over delta t, 16 times, and we want to know it at 2. Okay, well, 2 plus some h minus 16 times 2 over h. We want to calculate this as h gets closer and closer to 0, but we can't put in a 0. Right? So we want to take limit as h goes to 0. In other words, that's a limit, deal with it. as h goes to 0. This is what a limit looks like. This is what we're going to be doing a lot of, limits. All right. So, how do we do this? There's got to be some magic way we can do that. And we call this the long way. All right. So we multiply it all out. 16 times. Let's distribute this part. 4 plus 4h plus h squared minus 16 times 4 all over h. Well, check it out. 16 times 4, that's gone. And that leaves us with 16 times 4h plus h squared. I can pull an h out of each one of those. And leaves me with 16 times 4 plus h. We said we want h to get closer and closer to 0. We want to take a limit as h goes to 0. So we're just left with 64 feet per second. We have just taken our first derivative. We have just used what's called the, no, I don't remember it, quotient, difference quotient, something silly like that. Who cares? We have found that at t equals 2 seconds, if we were able to get a really, really good measuring device and say, what is the velocity at that instant, is 64 feet per second. The average over those first 2 seconds was 32, but at 2 seconds itself, 64. Oh boy, we got a lot to do. And notice we used velocity early on. Well, that's what Newton was doing. He was thinking about the laws of motion. So, all right, fine. Let's use an example from above to find the instantaneous velocity at t equals 2 seconds. I could have sworn that we just did that. So I will write, we just did that. All right, so let's write it properly. Limit as h approaches 0 of delta y over delta t. Notice they're deltas. When we do a derivative, we'll change them to lowercase d's. Is 64 feet per second. I always thought this was kind of the way I did limits, but when I've seen a lot of people's work, a lot of people do it that same way. All right, cool. Hey, we're on a roll. How about limit is actually, well, it looks hard. I don't, what? I'm so confused. Well, let's do something a little more difficult. I don't want to do something a little more difficult. I think that's stupid. Let's do it the smart way. Let's graph it. Okay. See if I get this to work here. And let's share our screen, which I think I forgot to the last time I did this. Very upsetting. Get you up out of the way, and y equals clear, clear. Alpha y equals fraction bar, sine of x over x. Graph. Limit as it approaches 0. It's getting closer and closer to 0. Wow, looks like it's hitting 1. And that's both coming from the right and coming from the left. That's foreshadowing. We're going to get into that later. Well, what if I looked at the table? It's up there at 1,000. Oh, we have to set the table. That's what Mom said. Let's go with -1, and let's go by 0.1s. And let's check out that table. Check it out. We're not allowed to divide by 0. Sure looks like it's getting closer and closer to 1, though. So this is where we're stuck early on. We can do this again. Second table set. Start at -0.9 and go by 0.01. Let's see what we get here. I don't know why I'm going up, but okay, I am. Boy, I got lost all of a sudden there. So I'm going the wrong way. That's hilarious. Now it's stuck. Oh no, it's broken. Oh, it's haunted. So we'll see if it stops eventually. Oh, it did. All right, cool. So I got to go down a lot. Nice to get confused and show people it happens to all of us. This is going to take forever. Let's wait till it stops, catches up. Second table set. Let's start at negative 0.9. Yeah, that should work. No, it didn't work. What am I doing wrong? 0.01. Oh, I know what I did wrong. Okay, second table set. That's so weird. Negative 0.1. Second table. There we go. All right, check it out. 99985, 99993, 99998. Error, because can't divide by 0. So check it out. I put this on a resume once. We can actually divide by 0 by taking a limit. Weird. This sure looks like it's going to 1. Huh, well, we're going to be doing this later. Might as well start now. Limit as h goes to 0 of sine of x plus h minus sine of x over h. I just proved it equals 1. I wonder if we can do that algebraically. That's also called foreshadowing, people, so that's coming later. Might not be a bad idea to memorize this for the time being. Very soon you will be able to calculate it in a very simple way, but not yet. So we need a definition. I am not going to get into this at all. The reason is I say as it gets closer and closer to 0. Well, how close? Well, just close. That's not good enough. So they do this whole thing as the distance between x, some value c becomes less than some delta, lowercase d, then the y-axis becomes less than some epsilon, and they say that's a definition for us. And the limit is L. Doesn't really help me very much, so I just kind of ignore it. It's certainly not on any test or any AP exam. So, but here we go. Let's see what's going on. So, x squared minus 1 over x minus 1. I happen to know this little graph is x plus 1. Let's go up to 1 with a hole at x equals 1. So we say, oh, the limit we'll call this one f of x, as x approaches 1 of f of x is 2. As we get closer and closer to 1 on the x-axis, the value from both directions gets closer and closer to 2. All right, get used to that. And you do this a lot. All right, sure, whatever you say. Let's try g of x. And g of x fills in the hole. It's the exact same thing, except it blew it, filled it in the wrong place. It made the dot down here at 1. So you would say, oh, the limit as x approaches 1 is 1. G of x, yeah, no, that's not it. It's very, very challenging to understand this. But what it means is, what does it look like it's about to hit? I don't care what it actually hits. What does it look like it's about to hit? Well, at 1, it looks like it's about to get to 2. So then it's still 2. Even though the function here is 1. Different animal. Calculus. Things are not set in stone. Get used to it. And then h, this one, what'd they do? No, it's just x plus 1. That's weird. I was looking at g of x. The limit as x approaches 1 of h of x is just 2. You say, but nothing's really happening there. Why would you suddenly write that? Because nothing's really happening there. Every now and then that happens. What's going on here? Nothing flashy. It's just, oh, okay. I guess it's going to 1. Sure, whatever you say. Limit properties. Read through them. I'm certainly not going to go through them in detail. So I wrote them down. All right. Limit of x, yeah, some rule. There's a problem that used some of this. Boy, it got confusion fast. Popped up once every 5 or 6 years. So really not something we're going to spend a ton of time on. But you can add your limits together. You can subtract them. Ooh, that looks wrong to me. think that would be L minus M. Have to fix it. L times M. Okay, there's a K out front. That one I actually use. I pop it out front. Divided as long as M doesn't equal 0. Yeah. So this is stupid. Just so you're aware. This equals 3 squared, 2 minus 3, negative 9. Now, I cannot overstate this. This was done wrong by about 40% of the people on the AP exam. They would rewrite this with the limit here as the numbers were put in. This is the proper way to show it. You don't write, oh, limit x approaches 3 and then plug the 3 in. That's wrong, and they lost points for it. Quite serious about it. Let me show you. So this is limit as x approaches 0. I am not putting in the 0. Sine of x over x times 1 over cosine of x, which we happen to know the first one is 1. See, now I'm not writing limit anymore, and 1 over cosine of 0 is 1, so 1. And this one equals limit as x approaches 1 of x minus 2, x minus 1, x plus 1, x minus 1, cancel, cancel. I can't put 1 in. It's going to create 0 on the bottom. I cancel. I can put 1 in. Equals, again, now I am writing it without a limit, negative 1/2. Cool. So I've commented on this a couple times. You can only find a limit if it approaches from both sides. We're actually going to do one-sided limits, which I think is really, really stupid, but you know, what are you going to do? So if you graph this, x approaches 2, you find there's an asymptote at 2, 1, 2. And on the right side, it does something like this or some weird thing. And on the other side, it does something like this or some weird thing. And we are going to cheat. We are at some point in time going to say limits go to infinity. So it's going to negative infinity or positive infinity. However, this one, as x approaches 2, on the right goes down, on the left goes down, on the right goes up. This does not exist. Mathematicians hate using the expression infinity because it's not very precise. So you will never see it on the AP exam, ever. But we're going to use it a little bit here just because it helps us illustrate what's going on. And really, it bugs some people. So they say, hey, let's say from the negative side. We'll put a little negative here. And the really horrible part about this is it's easily missed. I had seen this on the AP exam, extraordinarily rare, right? Let's see what's going on with 1 over x. Does this. All right, so as we approach 0 from the negative side, that means here we go to negative infinity. That is mathematically unsound, but you know, it's cool. We're all friends here. From the positive side, it goes to positive infinity, which is worse because we don't even write the positive. We just write infinity. But hey, from both sides, does not exist. So I gave you a little bit of practice. X approaches 1 from the negative side. So we'll come in from the negative side. It looks like we're about to hit 1. No. We're going to 1. And what is that on the y-axis? That's 0. Then 1 from the positive side, coming this way, that's going to be 1. It's getting closer and closer to 1. And it actually hits 1. We don't care. Getting closer and closer to 1. That's all we care about. 2 from the negative side is getting closer and closer to 1 also. 2 from the positive side is getting closer and closer to 1 also. Since it comes from the negative and positive, we could actually say the limit as x approaches 2 with no positive negatives of f of x is 1. And you're sitting there going, ow, my brain hurts. F of x is actually 2. How can a limit be 1 and the function be 2? Yeah, that's why we're practicing limits. And last but not least, the sandwich theorem. It's not on the AP exam. I put it in here because a lot of mathematicians get really jacked up about it. I had one guy go, oh, they had a sandwich theorem question on the AP. And I was like, really? I'm surprised. He said, well, it wasn't on the AP. It was on the questions the AP sent us to practice for the AP. So I said, it's not actually on the AP exam? He said, no. I said, okay, I'm not too worried about it. Oh, you should be careful. I'm like, shut up. So here's x squared. And here's negative x squared. And this, right, so this is, right, and it actually should go down, excuse me, and hit 1, hit 0. So it's actually drawn wrong. But I did it this way because this, if you graph it, does this from both sides. But it's always underneath and above the x squared functions. So that's why they call it the sandwich theorem. You can pick other functions, which is of course impossible for us to do as baby mathematicians. Oh, I'll just randomly pick some weird ass function. No, it doesn't work like that. And here's how they do the math. Well, the absolute value of x squared of sine, that's why we have both. And again, it should go down to 0. Do this sort of thing. Do this sort of thing. Sine of 1x is, you can break it up, some laws of limits. Sine of 1 over x, which is less than or equal to x squared. All right, absolute value of x squared is actually x squared because negatives cancel out. This is how they do it. I mean, this is the dumbest thing I've ever seen, and I think it's a nice little concept, but we don't need it. And again, it's just mathematicians getting really like, oh, let's talk about sandwich theorem because it's so cool. No, it's not. It's just confusing. So negative x squared is always on the bottom side. X squared is always on the top side. We just proved it up here. We didn't prove anything. Yeah, trust me. So the limit as x approaches 0 of negative x squared is the limit as x approaches 0 of x squared is 0. And therefore, limit as x approaches 0 of x squared times sine of 1 over x is 0. I am completely cheating. I'm using my old notes because otherwise there's no way I could do that. None whatsoever. And I consider myself fairly knowledgeable about AP calculus, so I'm not too worried about it. You could just cross all this out and not write it down if you want, but you can see why they call it sandwich theorem. You're sandwiching between two things. I don't like it. Among other things, I feel like it's a very limited thing. It'll pop up once or twice more. Just, hey, we can also use sandwich theorem to prove this. Big honking deal. That's it. Happy mathing.